right, last video for the year. Woohoo! Thermodynamics. That sounds very similar to Chapter 6, Thermochemistry. But now we're not just chemical, we are dynamic. Okay, don't worry about 18.1. Short little paragraph, not important. 18.2, spontaneous processes and entropy. So a spontaneous, when you hear spontaneous, you should think about what you know about that word. People can be spontaneous. They do things, they just do them spontaneously. That's what a spontaneous process is. It's something that just happens. It happens. You don't need to put work into it to make it happen. It just happens. And in fact, you will learn very shortly that when you have a spontaneous process, it can do work for you. Entropy is something totally different from spontaneous processes. It affects whether or not something is spontaneous. But entropy is a measure of how many different ways you can organize a system. A lot of books talk about entropy being a measure of disorder. It is not. Don't think of it that way, even though the comics I'm going to show you later do represent entropy as disordered. The real idea of entropy is how many different ways can you organize something? Well, if you have a lot of disorder, you could order that disorder in so many different ways that it has a lot of entropy. Whereas, let's just imagine you have a room full of red balls versus a room full of balls that have every single color that you could imagine. Well, the room with the red balls can all be arranged with the red balls all red. It's just sort of one way to organize that place. But if you have all sorts of colors that the balls are, then you could organize those balls in all sorts of different ways in that room. So that room would have a lot of entropy. Okay, hopefully that made some sense. Let's see. This is just repeating what I already said. A process is spontaneous if it occurs without continuous added energy. Sometimes a spark or initial amount of energy is needed to ignite the process if the activation energy is very large, but then the process continues on its own. So kinetics can affect the beginning of the reaction when we're talking about spontaneity and reactions here. So if you have a high activation energy, we might need something to start off a reaction, but if the reaction is spontaneous, it's just going to keep on going. And when a reaction is spontaneous, it is driven in the forward direction, and as I mentioned earlier, the reaction will be able to do work for you. It also means products are favored. So these three words, spontaneous, driven in the there's more than three words here. These three ideas. Spontaneous, driven in the forward direction, products being favored, four ideas, and ability to do work. These all go together. If the products are favored, the reaction can do work. If the reaction is driven in the forward direction, it can do work. If the reaction is spontaneous, the products are favored. These are all equal to one another. If one, then the other. As an example, have you ever seen a waterfall where the water runs uphill? I personally haven't. Waterfalls, the water just runs. It's spontaneous, and that waterfall can, in fact, do work for you. Another concept, when you put your sugar in your coffee, sometimes you spin your coffee to get the sugar to dissolve a little faster, but regardless, even if you didn't spin your little coffee cup, the sugar would dissolve. That means, since the sugar actually does dissolve, the dissolving process is what? It is spontaneous. All right, I'm going to fix some. Notice I just got rid of spontaneous processes and entropy in 18.2 because 18.2 is just spontaneous processes. Entropy, I've already talked a little bit about entropy. I told you about the red balls and the rainbow balls. The rainbow balls is the room filled with rainbow balls would have more entropy than the room filled with just red balls because there's different ways to organize the balls. So entropy is the number of different microstates in which a system can exist. You know, you can take an entire year class just on entropy, and it's really hard. So we're not going to go into statistical thermodynamics, which entropy is really about statistical thermodynamics. There's a lot of statistics in here. I'm just giving you a very simple definition. How many different ways can you organize a system? And the symbol for entropy is S, because doesn't this word entropy look like S? I have no idea why the symbol is S, but it is. Okay, oh, don't look at that yet. Probably have it in your notes, even though I don't have it written down here. So let's just think a solid, a liquid, a gas. When you have a solid, well, everything is stuck in space. It can't move around, now can it? So entropy is pretty low. The liquids, now in a liquid, the molecules can actually move from one place to another. And the molecules are a little bit farther apart typically. So there are many more ways to organize the energies and the actual placements of the molecules in a liquid. So a liquid should have more entropy than a solid. And now think about a gas. Well, in gases, there's energy being transferred constantly. When gas molecules smack into one another, energy is being transferred. Those gas molecules could be in so many different spaces because there's a lot of empty space. And those molecules can move all over the place within that space. So entropy of a solid is less than the entropy of a liquid, which is less than the entropy of a gas. The gas has the most entropy. Now think about an aqueous substance versus a solid substance. Versus a solid substance. Remember, aqueous is not a liquid. Aqueous means particles are dissolved in a liquid. Do you think that that should have high or low entropy when you have an aqueous solution? I don't have this written anywhere. You might want to write it down in your notes. It's just something to think about. And I hope you've thought about it. And so an aqueous solution would have pretty high entropy. For any spontaneous process, the entropy of the universe must increase. Not the entropy of a reaction, entropy of a universe. So the universe includes what's happening in a reaction and the surroundings of the reaction. So we have enthalpy coming into place also. And enthalpy affects the entropy of the surroundings. What this does mean that if delta S for a reaction, if that is larger than 0, that would help drive a reaction in the forward direction. So a positive delta S, and it's just like delta H where we have products minus reactants, delta S will be products minus reactants. If delta S is positive, the reaction would be driven forward by the entropy change. And here's just some entropy jokes to help you visualize entropy. So here we have a very messy room. It could have a lot of different microstates because this little skateboard could be over here and this shirt here could be over here. There is a lot of entropy and this little boy is saying the room is a mess because of entropy. Over here, let's try to read this. Entropy seminar. The results of a 5-year study into the of thermodynamics and its inevitable how shrews by something something. Well, that's what entropy is going to do. It's going to move your letters all around. This is just summarizing some things that have already been stated. The second law states that the entropy of the universe is constantly increasing. The third law states that the entropy of a perfect crystalline substance is 0 at absolute 0. So entropy has an absolute scale. At 0 Kelvin, absolute 0, particles are not even moving. They have no energy. And because they have no energy, they don't move. They can't transfer energy from one particle to another. And if there is a perfect crystalline structure, then you can't move the particles into another place. It would look you just couldn't reorganize it. So these perfect crystalline substances, absolute 0, have an entropy of 0. And the definition, I mentioned this earlier in words, but here we have the equation. The change in entropy of a reaction is the absolute. Notice there's no delta here for delta SF, whereas for H, enthalpy, you might remember we had delta HF. There's no such thing as delta SF because we have absolute scale for entropy. That little 0 there, the naught, that stands for standard conditions. 1 atmosphere pressure and 25 degrees Celsius, sorry. So entropy, delta S reaction, the standard entropy of a reaction change, standard entropy change for a reaction is the sum of the entropy of the products minus the sum of the entropy of the reactants. You should be able to do this as we did in the enthalpy chapter. Okay, so let's just look at some different problems here. We're going to think about whether entropy is increasing or decreasing. If we have more moles of gas in the products than the reactants, we go, fix that little typo there. More moles of gas and products. Who has more entropy, the products or the reactants? More moles of gas. The products have more entropy. So we have products more entropy minus less entropy should be a positive number. So delta S reaction is greater than 0. It's positive. So I want you to do these. I'm going to put the answers in here, and you can always ask me about it in class if you have any questions. So think about these. Pause this right now because I'm about to put in all the answers. All right, here's your answers. So dissolving a solid going to a liquid. Liquid is the product, has more entropy than a solid. So large minus small, greater than 0. Two solids combining into a single solid. So the product has only one solid. The reactant had two solids. If you're going from two solids to one solid, we're going to less entropy. Delta S is less than 0. So just think about the phases that these things are in and whether you're creating a gas or a liquid, etc. Okay, if delta S reaction is positive, did entropy increase or decrease? It increased. Okay, predict the sign of delta S for each of the following reactants. So pause if you want to do this on your own. I'll talk you through this. So solid going to aqueous, don't forget to pause right now. So this has more entropy, delta S is positive, entropy is increasing. Liquid to solid, delta S is negative. 2 moles of gas going to 3 moles of gas. 3 moles of gas has more entropy than 2 moles of gas, so entropy delta S is positive. To 3 moles of gas. Now we're going to ignore the solid here because the solid has less entropy than a gas, so it doesn't matter that there's 3 moles. You only count moles of gas. 3 moles of gas going to 2 moles of gas. 2 moles of gas has less entropy. Entropy decreased. Delta S is negative. Here's your answers. Okay, done with entropy for the moment. On to Gibbs free energy, G. Gibbs free energy is a measure of how much work a reaction can do, and it tells you if a reaction is spontaneous or not. You're going to see a whole lot of stuff now on Gibbs free energy. Gibbs was a famous chemist, physicist, who did work on spontaneity and reactions. Here's a summary of all of this. So just like the S and the delta S and delta H, delta G reaction, this should say reaction down here. If there's nothing down here, it's for a reaction. It's a sum of the delta G of formation of the products minus sum of delta G of formation of the reactants. So you've seen this over and over. Works for delta H, delta G, and delta H, delta S, and delta H. And delta G. I can't speak. We have this equation that relates Gibbs free energy, enthalpy, and entropy. It includes temperature. Delta G is delta H minus T delta S, where T is temperature. And Gibbs free energy is the energy available to do work. If delta G is less than 0, negative, the reaction is spontaneous and can do work. If delta G is greater than 0, the reaction is not spontaneous. You have to continuously put work into the reaction to make the reaction go. And if delta G is 0, we are at equilibrium. That is very... At equilibrium, delta G is 0. Okay, looking at this equation right here lets us know these two things. If delta H is greater than 0, if this is a positive number, and delta S is less than 0, minus, T is always positive, we're going to ignore T, because we're doing this in Kelvin. This temperature has to be in Kelvin. All right, so delta H is positive, greater than 0. Delta S is negative, so we're subtracting a negative number. If we have a positive minus a negative, that is equal to a positive plus a positive, right? Which is always greater than 0. Greater than 0, greater than 0, non-spontaneous. The reaction is never spontaneous. I want to pause for a moment. Okay, let's check this other one. If delta H is less than 0, we have a negative, and we're subtracting delta S is greater than 0, a positive. If we have a negative minus a positive, that's like a negative plus a negative, right? And if we have a negative plus a negative, that is always going to be less than 0. That will always be negative. Therefore, if delta H is less than 0, negative, and delta S is greater than 0, this positive over here, delta G is always less than 0, and the reaction is always spontaneous. You don't want to memorize either of these two sentences that I just wrote. You want to be able to analyze this equation, whoops, this equation right here. You want to analyze this looking at the sign of delta H and the sign of delta S, and think about, could delta G be positive, always negative, or sometimes positive, sometimes negative, depending on the temperature. The temperature will switch the reaction to be spontaneous or non-spontaneous in some situations. If delta H is positive and delta S is positive, then we don't ultimately know the sign of delta G, because we have a positive minus a positive. That's not equals, that's minus. A positive minus a positive depends on how big this positive is. If this positive is super big, then a positive minus a big positive would be less than 0. But if we have a big positive minus a little positive, then delta G is greater than 0. So at low temperatures, we'd have a delta G greater than 0. And in those situations, you have to actually think through the situation. Okay, so last thing here, and then we'll do a little practice on all of these. Free energy and chemical equilibrium. So we've been talking about equilibrium in the last few chapters. Now we're talking about free energy, and we're going to unite everything all together. So we have this equation right here, right there. We have that equation. We have this equation. And we can use either of those equations to calculate delta G. And then there's this other equation. Look at this. We just united Gibbs free energy, delta G. Oh, here's our equilibrium constant. This allows you to calculate Gibbs free energy from an equilibrium constant, or if we know Gibbs free energy, we can calculate an equilibrium constant, vice versa. To get rid of logarithms, you do e to the x. So e to the negative delta G over RT would be k. I don't have that written down. It's okay. We'll go through that. I'll write it down right now. E to the negative delta G over RT is equal to k. This equation and this equation over here, they give you the same, they're equivalent equations. We're just taking the inverse of the logarithm. And those two equations unite thermo and equilibrium. So if a reaction is spontaneous, delta G is less than 0, and then K is greater than 1. If a reaction is non-spontaneous, delta G is, did I say less than or greater than here? Sorry, I might have said that wrong. If a delta G is positive, greater than 0, K is less than 1 because the products are not favored. So spontaneous products are favored. K is greater than 1. Remember, K is products over reactants. This all makes sense. All right. Oh, don't forget Q, this Q here, that's our reaction quotient. Reaction quotient. That's if you are not at equilibrium. So this is at equilibrium, this is not at equilibrium. I had to also fix, we needed a little knot there for standard conditions. Okay. Moving on, we're going to try some of these. So notice we're given delta H, and then we're going to be given some entropy information, and you're going to try to figure these out. I'm going to just put the answers up here. You should pause this and try to think about it yourself, because the answers are going to show up in the next 5 seconds. So go ahead and pause. Okay, let's go through these real quick. Exothermic, negative delta H, exothermic. It's not endothermic. We have a positive delta S and negative delta H. Therefore, delta G is always negative. So this is always spontaneous. Adding a catalyst does nothing. All right, delta S is positive, so at higher temperatures, as T goes up, delta G becomes even more negative, so the reaction will be more spontaneous at higher temperatures. Okay, delta S surroundings, that's the enthalpy. Don't worry about F so much. You're probably confused. Since delta H is negative, delta S of the surroundings is indeed positive. O2, this is false. S is 0. That was the third law of thermodynamics, only at 0 Kelvin for pure crystalline solids. Activation energy. Okay, let's look at this. We have an exothermic reaction. So the activation energy graph looks like this. Remember, this is our reaction coordinate down here. I can't write that down. This is our energy. It's really badly written. Okay, the forward activation energy is actually less than the reverse activation energy. Ooh, the active is lower than the reactivation energy. That one is true too. Sorry about that. Because we have an exothermic reaction. I am human. By the way, there was this little note down here. So I had these notes for C, E, and F. They would have helped, you know, if I had pointed them out before you started this. But delta S surroundings is positive if our reaction is exothermic. That's how we knew the answer for F. Okay, so try these. And pause, because you're going to see the answers in just a moment. I will put them up. So pause. All right, I think I've got this right. Let's go through it. If you think you have it right, you don't have to listen to the explanation. The beaker got cold, which means this took in heat from the water, so endothermic. The reaction took in the heat. Entropy change. We went from a solid to things dissolved in a solid. Well, that is definitely an increase in entropy, so delta S is positive. All right, now in temperatures. If delta S is positive and delta H is positive, we need temperature to be large so that this piece is larger than this piece to get a negative delta H. That's why the dissolving is spontaneous at high temperatures. Okay, here's a problem. Delta H vaporization is given to you, and that would be the delta H right here. You're given your boiling point. This will be your temperature in this equation. To convert to Kelvin first. Find the entropy change for the vaporization of 50 grams of ethanol. Okay, so one important thing is if we're vaporizing, delta G is 0. This is an equilibrium process. So delta G is 0. We know T, we know delta S. This is 0, so delta H will equal T delta S. We can solve for delta H, and then we need the molar mass of ethanol. Ethanol is C2H5OH. So let's look at this. Try to set it up yourself, and here's the solution. You can see it. So delta G is 0, so we have this. Delta S, oh, we had delta H, I'm sorry. Yeah, we had delta H. We solve for delta S, plug in our numbers, and you have to make sure that your units are all correct. We need to use this, that's joules per mole Kelvin, convert our grams to moles, and then use our heat of vaporization to convert from moles to joules, and we get our entropy, joules per Kelvin. Okay. Okay, you are given delta S, which will be products minus reactants. Pure elements are no longer 0, so you just plug in this is equal to the products minus the reactants. You're supposed to calculate S for chlorine, so you'll have a 2x in your reactants. And, oh, you were given delta H, and you're asked for delta S. So I'm going to show you the answer. You should pause if you want to work this out on your own. Okay, there's your answer. And then there's going to be a part B here. Is this always, never, or sometimes spontaneous? We have a positive delta S and a negative delta H. Positive delta S, where did we go? Here we go. This is positive, this is negative. A negative minus a positive is always negative. Delta G negative is always spontaneous. There you go. Always spontaneous. Calculate delta G. We're just going to use the equation delta G is delta H minus T delta S. Be very careful with your units. These are in kilojoules. These are in joules. You want to make sure your answer, you do not mix units. So we just plug into our delta G is delta H minus T delta S equation. And now calculating K, we're just going to use this equation right here. Oops, one more page back. There we go. We're going to use this equation to calculate K. Remember to invert the equation, you need e to the negative delta G over RT. For R, you'll use 8.314 joules per mole Kelvin because G has the units of joules in it. So we have to do joules per mole Kelvin, use Kelvin for temperature. And if you would like to pause, you can, or I'm going to show you this right now. There you go. All right. Calculate the equilibrium constant at a different temperature. So this is no longer the standard delta G because we're changing the temperature. So in this equation right here, our temperature will change slightly. We're missing an e raised to the power here. There should be a, ln of k is equal to this. Oh no, we're good, we're good. This is ln of k, and then to get rid of ln, we need to do e to the power. So this is our k. Sorry, so we're going to change temperature, use Kelvin. Okay. Explain the difference between the equilibrium constants for D and E. Well, notice this is much larger than this when we increased the temperature. A smaller equilibrium constant means we're shifting over to the left, right? Smaller equilibrium, less products. By Le Chatelier, should we shift left? Let's look at that. Delta H is negative. The reaction is exothermic. As temperature goes up, the reaction should shift left. The equilibrium constant should be lower at higher temperatures, and indeed it was. That's it.